Okay, guys, you got to answer my questions. It's hard for me to teach without the dialogue. So, Romeo and Juliet problem and the leftover problems from the last homework. Any issues? Okay, then I expect you guys to submit it, or I mean, resubmit or actually do an additional submit. Okay, good to know, Joseph. Yeah, so that's what I'm saying. Just upload those problems in the new assignment as a new submission, and I'll make sure that we're on the same page. Okay, so let's do some warm-up problems and then some more interesting problems. So this is the warm-up. Just take a couple minutes, think about it, and somebody feel free to start explaining it on the whiteboard.
Do we get the length of the straw?
Yes. Oh, is it not? Yeah, it's L. Sorry about that.
All right.
Okay, can you elaborate? So I see that you wrote the center of mass velocity. How did you get a 4 here? Oh, that's a U. Okay, gotcha. Okay, so in what reference frame is it?
This is the labs frame.
Yeah, but this U is with respect to the straw.
With respect to... Oh, I see. Okay, then this is wrong.
Interesting. Somehow you got the right answer. It really puzzles me now. Oh, okay. Be careful. So
yeah, no, this only works if it's the same, right? Or
technically, you got the right number, but let me emphasize, your answer is this, right?
yeah.
But if you draw the picture, actually, which way does the straw move?
To the left.
So I see that you assume that, yeah, the heavier bug is on the left. So then the straw must move to the left. According to you, it's moved to the right. If you just take it naively, I guess. This answer is a positive displacement.
Oh, but then like you could just add the you can just say like the displacement of, wait, sorry. Yeah, you can add the velocity of the straw to each velocity, right?
And what is
To each
that?
the velocity of the bug in the lab frame.
Yeah, but what's the straw velocity?
Um, actually, yeah, the displacement is going to be L over 2 minus L over 3 because they have to meet in the middle, but then the middle of the straw coincides to the initial center of mass. So that's the reason.
So you're saying they met in the middle of the straw, but at the same time, they meet 1/3 of L from the original right end.
Yeah.
Okay, that's a way to find it. That's one way to find it. Folks, are you with us? So if you remember the result of the last problem with 2 kids in the swimming pool, it's almost the same thing. So this is L over 3, the displacement of the bugs. Okay. But we know they meet in the middle because with respect to the straw, they just meet in the middle, right? They move at the same speed. There is no reason they shouldn't meet in the middle. So this is L over 2. And that means this is the difference, which is L over 6. Does that make sense? Yeah. But you shouldn't have erased your calculation because it's actually a method. I guess the guys will now need to watch the recording. Or is there a quick way for undo the erasing? Okay. Yeah, let's keep it because, you know. Because you can get it from here as well. Just keep in mind that this is in the Strauss frame. Maybe not in Strauss frame. Maybe I shouldn't write that. Okay. I guess you can still make use of this calculation. Okay, I have another problem for you. But I'm thinking maybe we should just keep it for your homework. So it's slightly more sophisticated. So, but that's based on the similar ideas. Yeah, so let's keep it for the homework. That will become part of the new homework. Let's talk about something related to momentum. So you probably noticed that momentum and center of mass motion are very tightly related. And let me just show you one problem-solving method that That is actually pretty rich, as you'll see, but today we'll just scratch the surface of how to apply that method. So yeah, maybe it's a long title. Using momentum to analyze bounces. Once we learn angular momentum, we'll actually do much more. But for now, let's consider this sample problem. So you have a ball, like a racquetball. That goes to the floor at some angle. So tell me, what do you expect to happen when it bounces off? What kind of angle will it make with the normal? This is the normal. So it hits and then bounces back. This is theta initial, and this is theta final. This is velocity final. So tell me anything that you think is relevant for this scenario. How much do you know?
It should be the same.
Okay, so it's tempting to say that. So let's write it. Theta initial equals theta final. Now, this is indeed the case if, and let's write the two conditions for this to happen. First off, the collision needs to be elastic.
Elastic.
Yep, elastic. And there is no friction with the floor. Let's say this is mu. And if it's 0, then we're good. So folks, is it clear what elastic means here? Elastic means that the speed remains the same, right? Kinetic energy stays the same, which means speed remains the same. But also you need to know there is no friction. So what does friction do? Friction changes the horizontal velocity, okay? So let's assume there is friction. And let's assume that the collision is not elastic, but it's usually denoted by lowercase e, sometimes by some other letters. This is basically the, what's it called?
Restitution constant?
Exactly, restitution constant. That is, it has to do with the perpendicular component of velocity. So Vy final over Vy initial. I'll just put absolute value just in case. And just to be sure, these are my X and Y axes. So find theta phi. And of course, theta initial is also given. So how do we do that? Well, obviously, tangent theta final should be equal to Vy final over Vy initial. Oh, sorry, over Vx final. Actually, that's the other way around, because the angle is with respect to the normal. So Vx final over Vy. In any case, we need to somehow understand what these V's are, how they come about. So, Elvin, are you familiar with this problem?
I'm familiar with restitution, but I'm not exactly sure how friction plays into it.
Okay, anybody else? Okay, so this is what we'll do. So we basically, let's say V initial's speed is just V. Then we can write that V initial x equals V, let's be careful, sine theta initial. See, this angle is not measured with respect to the x-axis, it's measured with respect to the normal. And V initial y is V cosine theta initial. And then let's see what happens. We basically need to zoom in onto the collision with the wall, with the floor. So on the x-axis, we have the friction force. Let's basically, yeah, let's zoom in. Here. Friction is acting this way. And normal force is acting this way. I'm not doing it up to scale right now, just representing the force. And you can actually neglect force of gravity, because that's much, much less than the normal force during the balance. Normal force may be like hundreds and thousands times greater than the force of gravity. So the normal force changes the y momentum and friction changes the x momentum. So the way you can write it is the following. And say that delta V x equals force of friction over m times delta t. Does this make sense, folks? This is acceleration, the horizontal acceleration, and this is time. Okay? And we can write it as mu times normal force over m times delta t. Now, delta V y equals normal force over m delta t. Okay? So you see there is this combo that shows up in both places. Okay? So the rest is basically just a mechanical derivation. So we need to say that Vx final equals Vx initial plus delta Vx, which is Vx initial plus mu n for m delta t. And the same for y. Y initial plus N over M delta T. Okay. And then, of course, you form this ratio, you substitute the initials. In general, of course, it's hard to get the answer. You need to know like the normal force and the time. But if you assume that the collision is elastic for simplicity, then you know that Vy initial and Vy final are opposite to one another. Okay? So if we indeed make this assumption for now, then Vy final equals, it's positive, so it equals the absolute value of Vy initial. Okay? Then from here, which is the same as negative, and this is equal V times cosine theta initial. Okay, so if you substitute it in the second equation, you can solve for this combo. You see that? So this N over M delta T is simply 2 times V cosine theta initial. Make sense? And then you can substitute this in here and find that Vx final equals V times sine theta initial. I'm substituting Vx initial explicitly, plus mu 2 mu V cosine theta initial. Okay? And then everything is given, like everything is known. You can plug things in this formula on top and get the answer. So the V's cancel. So you get sine theta initial sine theta initial plus 2 mu cos theta initial divided by 2 by V by cos theta initial. Does this make sense, folks? We can probably just massage it a little bit more and say that this is tangent of theta initial plus something extra, plus 2 mu, plus 2 mu, yeah. So you see that there is a change in the tangent equal to mu. So if collision is not elastic, then you just modify it a little bit more. right? So instead of factor of 2 here, you would have 1 plus e. So if not elastic, then v delta vy equals 1 plus e v cos theta initial. Okay, so you replace the 2 in here with 1 plus e. And that goes in here and eventually in here. And in here. Okay, folks, are you with me? Okay, that's how you can like consider the micro view of the bounds. And when you play pool, you may notice that the reflection angle is not always equal to the incidence angle. Does that correlate with your experience? Well, in addition, when playing pool, the balls can be spinning. And that's a whole different story. And that we'll consider as well, but like I said, we'll need to learn a little bit about angular momentum. So this is something we'll be doing on Thursday, okay? For now, we'll just pause here, okay? I want you to review this carefully and understand what ingredients came in. And I ask you a provocative question. This is for you to think at home by Thursday. What implicit assumption did we also make to get this? Well, maybe not so implicit, but we didn't really discuss it. What implicit assumption have we made? Yeah, Zoom doesn't allow me to write here. Yeah, this is a forbidden area for me, sorry. Okay, folks. Let me quickly survey you. Do you have an intuitive idea what could that be? You can put it in the private chat. I just, no, ignoring gravity is fine. Like I said, gravity is negligible compared to the normal force. Did we do estimate the other day? So assume that the bounce actually takes a few milliseconds. And the speed changes by, say, a few meters per second. Then the acceleration is like thousands of meters per second squared. Or like order of magnitude is 1,000 meters per second squared. Okay? That's much, much greater than g, which is 10 meters per second. So ignoring gravity is perfectly okay. That's not a huge assumption. So Joseph Vincent, do you have any intuitive idea what we assume that it's not actually obvious that we should assume that? Or it's not obvious that it should be true? Well, think about it. Actually, as a hint, there is a similar assumption that you need to do in that homework problem that I just showed you in the previous slide. So there is a similar assumption. Well, again, you need to recognize that it is an assumption and that it may or may not be true. Okay? So we'll start our discussion with that on Thursday, but I want you to give it a thought and see how far you can get. In theory, you can actually understand that just by carefully analyzing each step in the solution and see what exactly we had to assume. Okay? Just apply your best critique to this solution and tell me what could have not gone through. Okay, so let's come back to the idea of center of mass. Welcome back. So last time we discussed point particles. And we came up with this formula. The position of center of mass is given by m1 x1 plus so on mn xn over the total mass. m1 plus so on mn. So this is for point particle. But what if we have a distributed object? How do we handle it? So, object that has some weird shape and weird mass distribution. First off, what do we need to know? Yeah, clearly we'll need some integrals, that's true. But let's first understand what do we need to know to begin with to be able to answer this question, to be able to find the center of mass. So what do we need to know? We need to know the mass distribution. And that is described by a function, yes, exactly, called mass density. Or simply density. Once we switch to electricity, we'll also talk about charge density. That in that case, we'll have to distinguish. But by default, if you say density, that means mass density. Okay, so what is a mass density? As you know, if the object is uniform, the mass density is just given by mass over volume. But if the object is not uniform, what do you do? And by the way, this is a Greek letter rho. What if the object is not uniform? Well, that means density is not the same at different places in the object, but at each place, you basically zoom in, zoom in, zoom in, zoom in, and if you zoom in enough, calculus tells you that the density should be more or less uniform within that little piece of the object. Okay, so you zoom in onto this piece and you find its mass. Let's call it dm, infinitesimally small mass. It occupies infinitesimally small volume. Then you just take the ratio and that what you call local density. Okay, it looks like a derivative, and in many aspects it actually is some kind of derivative. So it's dm dv. So this is called volume density or bulk density. In addition to this, we'll also deal with sigma, which is surface mass density. That is similarly defined dm dA. Surface density. And lambda, which is linear density. dm dl or dm dx, depending on how you label your length. This is called linear density. Okay. Are you guys familiar with all these letters? Sigma, lowercase sigma, and oh, what's lambda? Okay. Now, okay, suppose you do know this density at every location. So that means you know this function x of y, x, y, and z, rho of x, y, and z, okay? That label the position of the point. And then, of course, you need to visualize this object as a collection of point particles, each of them being a really small piece at some different coordinates. Okay, thank you, Vincent. So treat it as a collection of point particles. So each m1 and x1 in this formula would then be the coordinates of those pieces, and you need to add them up. Now, assume that, and of course you can write similar formulas for the y and z of the center of mass, right? That's no brainer. But how do we treat this? So obviously the meaning of this guy is the total mass still. And if you're adding all these pieces, then what you do is a simple integral. So I'm going to write it down. M, the total mass. And the way you compute it is, as Elvin described earlier, you integrate, right? From here, you can write that dm of the given piece can be found by taking the density at that location times the volume, okay? So integrate of rho of x, y, z, d volume. And in general, this is actually a three-dimensional integral, right? Over the object. So again, this is not mathematically precise. You still need to do what's called parametrization. You need to parameterize the boundary of the object. And in general, it may actually be pretty sophisticated. So in order to save our time, I just say we integrate over that three-dimensional region occupied by the object. Now, what is dV? dV is the volume element, the infinitesimal volume that's expressed in terms of the infinitesimal changes of the coordinates. So if you stick with the Cartesian coordinates, then this dV is simply the volume of the parallelepiped formed by dx, dy, and dz. So it's just simply the product of dx, dy, and dz. If you use spherical coordinates or polar coordinates or some other coordinates, it will be some other expression in terms of those coordinates. Again, I'm not sure how far in calculus you've got, but have you guys dealt with spherical coordinates or cylindrical coordinates? No? Okay, we won't go there. We won't go there. Let's just stick with Cartesian coordinates. All you need to know about them is that this volume is simply the product, dx, dy, dz. So then you write that mass equals, again, mathematicians always put triple integral in physics. We usually don't care. We put a single integral sign. As long as you specify what you integrate over, you don't really care how many integral signs you put. So over the object of rho of x, y, z, dx, dy, dz. Okay, so this is how you compute the total mass sitting in the denominator. So once you know the function rho, it's computable. Okay, how do you do the numerator? Well, in a very similar way. The only difference is that you put an extra factor of x in there, okay? So the numerator equals triple integral over the same object of x times rho of x, y, z, dx, dy, dz. And you have to repeat this integral for each of the three coordinates. You substitute y and z in order to compute the y and z coordinates of the center of mass. Does that make sense? Okay. In non-Cartesian coordinates, it's a little bit tricky. Say if you want to find the, you probably know in spherical coordinates, you have radius and you have two angles. So in order to find the radius, you have one formula. In order to find the mean angles, you have some other formulas. They're not as symmetric as the Cartesian coordinates, which is expected, right? Distance is very different from angle. So the formula should be different as well. Okay. So this is the math behind it. We can consider some examples now. I know you may not be super familiar with multidimensional integrals, so we'll stick with one dimension, okay? So one-dimensional object can be thought of as a rod, okay? And first, let's consider a uniform rod. Just because we know the answer, and we can use this integral approach to see if it gets us the right answer. And once it does, we should be convinced that the formula is meaningful. So let's say this is the rod, and we put the origin at the left end of the rod. This is the x-axis, this is 0, this is L. Then we know the answer, right? We know the answer that the center of mass of the rod is what? 1/2 L, right? In the middle of the rod. So well, let's do the integrals and see how they work out to give us this answer. And then we'll switch to more interesting examples. So what are we given? Uniform rod means we're given rho, and x is the only relevant coordinate here. So rho of x equals some, let's say rho naught, and that's a constant. We're given L, obviously. And we want to find the x. Okay, folks, based on your intuition, do you think the value of rho naught is relevant? No, right? That's what we discussed. If you rescale all the masses by the same factor, it doesn't change anything. Besides, if you have a wooden meter stick or metal meter stick, and let's say both of them are uniform, doesn't matter which one is heavier or lighter, the center of mass is still in the middle. So the value of rho naught is not really important. What's important is the fact that it's constant, okay? Well, let's do it. So the numerator, or maybe let's start with denominator. Denominator, we need to write the integral, one-dimensional integral. Now, instead of, actually, I should be using rho, my bad. Should be using lambda because it's a one-dimensional thing. So let me fix that. Okay, so we integrate lambda of x dx, much in the spirit of the previous page. Just look at it. Instead of rho, we put lambda, and instead of triple integral, we have just regular single integral dx. Now, over the object, what does that mean in one dimension? In one dimension, it simply means the limits of integration from 0 to L. Okay? So now we know that this is lambda naught. We can factor it out of the integral and have lambda naught integral of dx from 0 to L. And obviously this integral is just L, right? So this is lambda naught L. So far, so good? Okay, now the numerator. Integral from 0 to L, x times lambda of x dx. Again, factor out lambda, the integral from 0 to L, x dx. Now, what is this integral?
X squared over 2.
Yeah, but it's not just x squared over 2. It's x squared over 2 with a substitution from 0 to L. And at the upper limit, that gives you L squared over 2. The lower limit, it gives you 0. So the result is lambda times L squared over 2. Okay? And then the center of mass is numerator over denominator, which is lambda naught L squared over 2 over lambda naught over L times L, which simplifies to L over 2. Are we good? Okay. Now let's consider non-uniform rod. Non-uniform rod. So let's put some specific function. Lambda of x, let's say it's a linear function, not constant anymore, but a linear function, which I'll write as some lambda naught x over L, just to keep the units obviously correct, okay? As you suspect, again, lambda naught is not gonna matter. What's gonna matter is the fact that it's a specific function. And of course, L is given. Find position of central mass. Before we do the integrals, what do you guys expect? Like roughly, where on the rod will the center of mass be?
No, it's going to be skewed to the right.
Okay, toward the heavier end, right? Because this density is increasing. Yeah, if you were to draw the graph, lambda of x, oops. X. So some function like this. Okay. So the density increases to the right, and that's where we expect center of mass to be. Any wild guesses as to where it is precisely? You know what?
Lambda naught would actually matter here, right?
You think so?
Yeah, because if lambda naught is like really big, then it would be like to the right. So it would be more to the right. So
yeah, but big lambda naught would mean that the masses here would also increase proportionally.
oh yeah.
I'm trying to put these pictures under each other in a consistent manner, okay? So this is 0, this is L. You'll see that you actually have stronger intuition than you expect.
It should be at the centroid of that triangle, like whatever.
And where is it?
2 to 1.
2 to 1. Does everybody know the term centroid? for triangles? Okay, I assume yes. Yeah, 2/3. Look, the height doesn't really matter because this is just the function lambda. But lengthwise, yes. This is 2/3 L. Okay, this is what we expect. And then let's do the integral and see if our expectation comes true. So the denominator, the total mass, is the integral from 0 to L lambda of x dx, which is integral from 0 to L lambda naught x over L dx. Yeah, so lambda over L can be factored out. These are constants. 0 to L. This integral we already computed. This is L squared over 2. So by simplifying a little bit, we get lambda naught L over 2. Okay? Now let's do the numerator. Integral from 0 to L lambda of x times x dx. We can factor out the lambda over L. We have integral from 0 to L. Now we have an extra x that makes it x squared dx. And what is this integral?
It becomes L to the 3rd over 3.
Yep. So this whole thing becomes lambda canceling one factor of L gets us lambda naught L squared over 3. And finally, the position of center of mass, which is numerator over denominator. What does it give us?
2/3 L.
2/3 L. Very good. Okay. Any questions, folks? So let's come back to this picture. So think of what you, I know, so let's put this. We will find centers of mass of two-dimensional shapes, but we won't really compute two-dimensional integrals. That I promise. However, what we just found together can be interpreted as finding the center of mass of this triangular two-dimensional uniform slab. Does that make sense? So imagine you have this two-dimensional triangular slab, uniform, and you collapse it onto the x-axis. That would become a rod, but non-uniform one, with a density that actually increases linearly from left end to the right. Does that make sense? So this is it. As a side effect of what you just did, you also found the center of mass of a two-dimensional shape. Now, what if you had a cone, like with the axis parallel to the x-axis? A cone. Where do you think, or what would we need to do, and where would the center of mass be? Can you guess? So, folks, what are you thinking? Share with me.
Can you present like each layer as like a small disk?
Okay.
Right. So then like the quote unquote mass of each disk is some density times pi r squared.
Okay.
Right, and then you integrate that over r, because if
Okay,
you
well, don't integrate yet. Don't integrate yet. Tell me what the density function would look like, lambda of x. If you were to collapse that cone onto its axis, that would again become a rod, but non-uniform one. What would be the density looking like?
so you would know the ratio between the radius and the the x coordinate, right?
Uh-huh.
Yeah, so then at each x you have some r of x, and then it would just be
Okay.
like pi times r of x, pi times r of x squared
Okay.
times the volume density.
Okay, here we go. So let me first write this. R is that transversal radius of the cone, okay? And then R is proportional. Folks, is this obvious that R itself is proportional to X? The further you move from the left end, the proportionally larger the radius becomes, because it's all like similar triangles. So this is in turn proportional to X squared then. So lambda of X would look like some constant, let me call it C for now, times X squared. And the nice thing about it is that we don't care what the C is. Remember, rescaling doesn't affect the center of mass position. All you really need to know is this power. As soon as you know the power, you're actually good to go. Now, if we were to update these integrals, what would happen? You would put x squared in here, right? That integral would compute it down below. That would make it L over 3. Yeah. In fact, if we don't care about the dimension full things and only care about the numerical factors, that would give us 1/3, wouldn't it? And instead of 1/3 here, we would get what? Because this would have become x cubed, right?
Oh, so you just got like 4 over 3 for the center of mass.
And the answer, yes. And the answer for the cone would be 3, well, I would say 3 over 4, right? 3 over 4L. Does that make sense, folks? And again, look, we didn't compute three-dimensional integrals that you would have to do if you were to do it like rigorously. Okay, but yes, you can handle cones now, 3D objects. Is that consistent with your, like, well, I'm not sure if you ever did this before. So you knew the centroid of a triangle, that it's like 2 to 1, but I'm not sure if you ever dealt with 3D shapes in high school. Have you? No. Okay. We'll actually do something related to geometry after a short break. So do you guys have any questions? If not, let's take a 10-minute break, but if you do, ask them now. No? Okay, let's take a 10-minute break. I'll see you in 10 minutes. Okay. So yes, I promised we won't compute 2 or 3-dimensional integrals, but I didn't promise that we won't consider 2 or 3-dimensional shapes. Okay, so we'll learn some smart tricks how to avoid 2 and 3-dimensional integration. but we'll still consider those shapes. Let me first start with some examples that require no integration whatsoever. And you tell me if you've seen this before. You have a disk, and out of this disk, you cut a circular hole whose radius is precisely half of that of the original disk. Okay. Like Calvin is having issues. So disk with a hole. Or is the radius of the disk, and that's given. Find the position of center of mass of this shape. Position of center of mass. Okay, any thoughts? Maybe just expectations. Yeah.
We can consider the center of mass of the circle without the cutout, and then the center of mass of the cutout. So like assuming
you're breaking. Is it just me? Guys, can you hear Elvin? Elvin is like froze for me. Oh. Can you hear me? For me, Elvin is frozen. Elvin, say something. Yeah, okay, yes, exactly. Have you guys seen this problem before, or you just realize how to do it?
hello, can you hear me?
Yeah, you're back, thanks. Joseph, Vincent, Ellen, have you seen this problem before?
Yeah.
Okay, then we'll do it quick. There are actually two ways to approach it. The faster one is a little bit counterintuitive, but if you can live with that, then that's like a fast way to get the solution. And the way you do it is indeed, as you mentioned. I'm going to write an equation that you may or may not have seen before. Equation is like this. Equals the whole disk plus a negative mass. Okay, so let's say this is big M and this is negative mass, and then this is, tell me what little m is in terms of big M. how much of the big mass is the little one. So this is R over 2, right? So what is this ratio?
Alvin just got kicked.
Yeah, but can he get back? Is he writing you?
I'm gonna try to see if I can reach out to him another way.
Mm-hmm. Yeah, yes, Vincent, this is 1/4. Very good. So, and then you can just, oh, first off, let's talk about symmetry. So this is obviously a symmetric situation. I don't remember if we talked about it or not, but if you found that your object has an axis of symmetry, then the center of mass must be on that axis of symmetry. So clearly this object is symmetric around the y-axis. Therefore, the center of mass must be on the y-axis, which means the x coordinate is 0, right? So by symmetry, x is 0. Oh, and by the way, what do you expect of the y? Where is it roughly? Folks, where on the y-axis do you expect the center of mass to be? Positive y-axis. So somewhere here inside the hole. Down here, according to Alvin. Oh, I just realized that Vincent was writing to me only. Okay, so we have two different opinions. Guys, talk to each other. Vincent and Alvin. Yeah, Alvin, we started doing this. I just want you to argue, you and Vincent. Oh, okay. Looks like Vincent agrees with you now. Yes, indeed, because if you just like imagine cutting the shape into halves by the x-axis, obviously there is more mass below the axis than above, so the center of mass must be below the axis as well. So this is a clear expectation that the answer should be negative, and then now let's follow this this solution. So first off, we can say that there are two objects that compose this object of interest. So this has coordinate y1 for the center of mass, which is here, right? And this has coordinate y2 for the center of mass, which is here. So with respect to the y-axis, let me actually put it in this figure as well. So this is the y-axis. It's convenient to put the origin here in the middle of the original disk. And then that would make y1 0 and y2 would be r over 2, right? Now the masses we already wrote, m1 is big M M2 is negative M over 4, as we just found, right? So that's pretty much it. Let's substitute it in your favorite formula. The center of mass position equals M1 Y1 plus M2 Y2 over M1 plus M2. So if we substitute all these things above, we get, well, the first term is 0. The second term, M2, we get minus M over 4. Y2 is R over 2. And on the bottom, we have 3/4 of M. So if we do the math here, what do we get? Now we got 2 Alvins. Welcome back. So what do we get for the answer? Guys, can you hear me? Okay, thank you, Alvin. Yes, minus R over 6. Okay, yeah, this is a fun result. That's, and indeed it's negative. Okay, folks, any questions? So the idea now is that if you have some tricky shape that can be viewed as a, like, you know, bunch of holes in some easy object, then this is the approach you can take. You can think of the holes as putting negative masses on top of some original object without the holes, okay? Well, now let's get to some things that do require integration. Let's consider a semi-disk. Or no, semi-ring for now. Yeah, let me just stop here to making it worse. So this is a uniform semi-ring. And again, once we recognize it has an axis of symmetry, we can put the y-axis to go through that and argue that the x coordinate is 0 again. So what are we given? We're given the radius again. This is the radius. It's given. Find the y of center of mass. Again, we know that x is 0 again. Okay, again, any expectations as to where it should be, roughly, before we do the math? Oh, well, obviously between 0 and r, can you be a little bit more specific? Let's say, is it going to be at the middle, below the middle, or above the middle of r? Okay, I see lower. Does anybody think it's above? Okay, where do you think there is more mass? Just asking. Okay, well, let's put it down as our expectation and see if it works out. So how do we approach this problem? Does anybody actually want to maybe explain this problem? How about I give you 2 minutes, and if nobody wants to do it in 2 minutes, I'll do it. Oh, what is that? I'm just not familiar. I guess I can take the remaining minute and Google it. I don't think I ever heard of this theorem before. Oh, interesting. Interesting, I've never known it. Okay, I learned something today. Okay, so you're suggesting to rotate that semi-ring around the axis to get a sphere and say that the volume of the sphere would be equal to the volume, would be equal to the area of the semi disk. Actually, well, yeah, it has to be a semi-disk for the theorem to apply on it. Actually, we'll stick to that because we'll do the semi-disk next. But it doesn't seem to apply right now yet. What do you call? Alvin, are you referring to the Pappus theorem or something else? Well, I guess I need to check into what's happening with it. What does it do with the density? But okay, let me switch back to the problem at hand. Does anybody want to do it? No? Okay, I'll do it. So let's visualize this semi-ring as a collection of point particles. I'm going to pick some representative particle somewhere. And I will, actually, it's easiest to label its position on the semi-ring using the angle from the x-axis. So I'm going to consider this angle, theta, and that theta, which ranges from 0, well, technically it ranges from 0 to pi, but this quarter of the ring is actually going to do exactly the same thing as this quarter of the ring. So do you see we can just limit ourselves to pi over 2? Okay, let's do that. So we're going to make theta range in here from 0 to pi over 2. And this theta is the label for the particles, label for the position of the particles. So labels the point particles. Now, this point particle, in fact, spans a certain angle, tiny angle that I'll call d theta. Now, is it obvious that the amount of mass spanned by d theta is proportional to d theta? No, not obvious? We assume this is uniform. It's uniformly spread throughout the whole pi gradient. I mean, it's like having a uniform meter stick. If you cut a certain piece of it, let's say cut out 1 centimeter, you know it's 1/100th of the total mass, right? If you cut out 2 centimeters, it's 2/100ths and so on. So we can say that the amount of mass sitting here, dm, over the total mass equals the amount of angle spanned over the total angle. Now, the total angle here is pi, because we would take the whole shape, okay? So that means the dm is equal to m over pi d theta. Now, folks, a funny question. What would you call this combo? Let's give it a name. You can either say or type it. Any ideas? Okay, I would call it angular. I agree with the second word, Alvin, because it is indeed a density, but it's not radial, it's angular, right? It's per angle. Yes, so this is angular density, but we don't really care what this constant is. Remember, the factor doesn't matter. So we got dm of each piece. Okay, what else do we need? We need the y coordinate of each piece. So this is the mass of each point particle. Now we need the y, and the y is just r sine theta. So this is the y of each point particle. And then you can basically construct the integral formula. Right? You can say that y equals the integral. You integrate yeah, let me put it over the, maybe not. Let's put the limits already. The limits are from 0 to pi over 2, right? We're only doing the quarter here. On the bottom, we just have dm's, and we'll explain what that means later. And on top, we have a similar integral with dm times y, okay? And yeah, let's call it numerator over denominator and compute them. So denominator is the integral from 0 to pi over 2. What is dm? dm is right here, right? M over pi d theta. So this is a constant, goes out of the integral. When you integrate d theta, you get theta with a substitution from 0 to pi over 2. That is pi over 2. So you get pi over 2 times m over pi, which is really m over 2, which is no brainer, right? It's half of the mass. Exactly. So now let's do the numerator. Integral from 0 to pi over 2. Yeah, let's put m over pi outside. And then we have sine r sine theta d theta. R is also constant, so we can just pull it out. Mr over pi over 2. Now, what is this integral? Sine theta d theta.
Negative cosine.
Negative cosine. And then when you substitute from 0 to pi, what do you get?
It's like 2, right?
Cosine theta from 0 to pi over 2. Yeah, negative.
Oh, it's just 1.
Just 1, exactly. So we get mr over pi over 2. Wait, why did I put pi over 2 in here? Did something silly. Just pi, and yeah, this is just pi. Okay, now let's put it together. The y, which is n over d, what do we get? R times n over d, right? So you take this and divide by this. 2 goes on top, so it's actually 2 over pi. Do you agree, guys? Joseph, Vincent? Okay, so now, thanks, Joseph. So what is this number? Is this consistent with our expectation here? So 2 over pi versus 1/2. What is greater? Two over pi, yes. So this is greater than this. So in fact, the center of mass is actually above the middle, somewhere here. Okay. Again, folks, the way to understand that is just slice this picture horizontally and see where there is more mass. again, when you go through center of mass precisely, there should be equal amount of mass above and below the line. But you just think about it. The line has to be above the middle, because if you put it in the middle, there is more mass here than here. Is it obvious, folks? Just visually, I mean? Yeah, so visually it's obvious that if you put the line in the middle, there is more mass above. So the line, the center of mass has to be moved up. Okay. So that's nice, that's good to know. So remember this answer, we'll use it in the next page. Oops. Uniform semi-disk. So again, you guys can quickly use Pappus theorem and tell me the answer, and then we'll actually compute it. Given R fine. So what does the theorem say? So the volume of the sphere should equal to the area of the disk, or semi-disk, times S. So this is what, 4/3 pi r cubed. The area is 1/2 pi r squared. And the distance traveled should be what, 2 pi times y, isn't it? You guys with me here? Okay, then what does it give us for the y? For thirds? Pi r? Oh, yeah, right. 4r over 3 pi. Okay, so this is what we expect. Now let's do it the hard way. Well, maybe not so hard. So you probably understand that the idea is to break the new object into smaller objects that we studied very well. Okay? If you know nothing, you do it by brute force, you break the object into point particles. But we know something already. So what do you think we could do with this semi-disk?
You can turn it into a non-uniform rod.
Oh, and do one-dimensional integral?
Yeah.
We could, that's one way. Maybe you take some time and do it. I'm looking for some smart trick here based on the knowledge we've just obtained.
Yeah, I used the ring, right? And then I split it up into a bunch of rings. So then, and then each ring has a center of mass, and then that's the rod that I used.
Oh, when you say rod, you mean a semi-ring? Like a bent rod? First, I thought you suggested to collapse it onto a non-uniform straight rod.
I kind of see. Yeah, you can make it into one rod. I mean, one semi-ring, and then by taking the midpoint of each like radius. As it goes around.
I see.
Right, or?
I mean, that may work. Let me tell you what I'm thinking here. Since we know everything about a semi-ring, let's visualize this disk as a semi-disk as a collection of semi-rings, ranging in size from 0 size to R. Okay, so let me just pick some representative semi-ring, this guy. Okay, and let's write it down. So the semi-disk, semi-disk is a collection of semi-rings. Now we need to come up with a nice way of labeling the objects. Like in the previous problem, we put the angle as the label, right? Because each angle specifies uniquely the point on the ring. And in here, the straightforward way to label the semi-rings is to use their radius, R, okay? So R ranges from 0 to big R, and this is the label for the semi-rings. R comes with a thickness. Each ring comes with a thickness. Let us call it dr. So dr is the thickness of each semi-ring. Now, the center of mass position, let's call it y of r. What is it? Just read off the previous answer. That was r times 2 over pi, right? And again, this like even the answer from last time doesn't even matter. Do you see that? It's again a constant. All we need to know is that it's proportional to the radius. That's all. So we could have skipped the previous problem and still done this one. So what else? We need to know the mass. We need to know the mass. Let's do that. How do we get the mass, folks?
You can assign some linear mass density to the semi-ring. Cancel out somewhere. Okay,
again, I want to emphasize the approach I took last time. So think of some kind of proportion. Well, not exactly, Vincent, not exactly, but it is proportional to the area, that's for sure, because it's a two-dimensional object. Area is the relevant dimension for the mass. If it helps, we can set up a proportion. So the the amount of mass in the semi-ring over the total mass. It's going to be the area of the semi-ring, the green area, okay, over the area total. That make sense? Folks, are you with me on this? Okay, now let's just plug and check. What is big M? Well, we keep the big M, right? We just need to find this ratio. What is this dA? The green area, what is it? Again, if you're not, it looks like you haven't seen this idea before, so let me explain. Think of this as a bent rectangle. Again, it may sound as oxymoron to you, but think about it. If you bend a rectangle, in general, the area will get deformed. But if it's infinitesimally thin, which this green one is, it doesn't get deformed. So if the area of the rectangle is simply base times height, you bend it, it still stays the same. So bottom line is that exactly, it's the thickness, which is dr, times r pi. R pi is the base, which is half circumference, pi r. And this is easy. A total is 1/2 pi r squared. Just don't get confused between little r and big R. Okay? So let's put it up. We have, just massage it a little bit. We have m times, let's put all the constants in here, r dr over, and I can put a 2 in here, r squared. Again, remember, these constants don't matter at all. You only see how m depends on the variables, which are here. R dr is the main piece of this formula. Now we have all the ingredients to set things up. So I'm reminding you that y equals numerator over denominator. The denominator is simply the total mass. You integrate all dm's. Now let's elaborate. So dm is this combo, that is 2m over r squared integral of r dr. Now, what is the range of r? Well, already put it up here, notice. Very convenient. Put 0 to r. Okay? Now, this integral is very easy to compute. This is r squared over 2. So we get m. Again, that's it's kind of silly to do this integral. You can think of it as a checkpoint. You should get m at the end. Okay, if you don't, that means you made a mistake somewhere. Now, the non-trivial integral is the other one. So you need to integrate y dm. Okay, so it's a very similar integral. Same constant in front, 2m over r squared, the integral from 0 to r. And y is here, right? This is the y, okay, that we need to put. R over 2 pi times r dr. And again, you can factor out all the constants. What is the integral inside? So I'm putting the constants now. 4m over pi r squared. And what is the integral?
R to the 3rd over 3.
Yep. Very good. So yeah, let's just simplify it. Cancel a factor of r squared. So we get 4m over pi r over 3. Or here. Okay. Now from here, we get that y equals n divided by d, which is just m. So we get 4r over 3 pi. Is that right, folks? Is that what we expected? Good for the theorem. It works. Okay, any questions? Well, I have a homework question for you. Well, let me give it to you and you tell me if it's too hard next time. If it's too hard, then well, we'll just talk, we'll discuss it together. Find center of mass of a hollow hemisphere, like very thin hemisphere. And find center of mass of solid uniform hemisphere. Okay. Again, naively, that would require 3D integrals, but you're now smart. You've learned some techniques. You should be able to do it using at most 1D integrals. Okay. Folks, any questions at all about today's class? Okay, so I'm going to post this probably later tonight because I have another class, but I'll post the notes. I'll post the recording as soon as it becomes available. You try all these problems by Wednesday night and we'll discuss, like we'll start Thursday class by discussing them. Quick question to everybody. Do you guys also participate in math Olympiads? Okay, so
Olympiad contests.
Well, contests. Okay, so I'm just curious. Are you familiar with the method in geometry that's called barycentric method or center of mass method? It goes either way, center of mass or barycentric method.
Barycentric coordinates.
That is related. That is related to that. But it's the method is mostly about either finding or about proving or finding certain ratios or proving that, say, certain lines intersect at the same point or planes in 3D. You can actually do stuff in 3D as well. Let me give you like the very basic problem that uses the method, and you can tell me if you like know what to do or not. So you probably know the answer, but I'm not sure if you know the method. Consider 3-point particles of arbitrary mass. Actually, let's consider equal masses for the sake of the example. And like I said, these are totally never mind. These are totally like arbitrary triangle, arbitrary sides. It's not equilateral in any way. So say M1 is the same as M2, M3. Let's say M, but the sides are arbitrary. Where is the center of mass?
At the centroid. And
that is where? Like a little bit more descriptive.
Well, you take the coordinates of M1, M2, and M3, and then you basically average to the X and average to the Y coordinates.
Okay, that's fine. That's fine. We all know that. We know the formula. But using purely geometric terms, where is it?
What, the intersection of the medians?
Exactly, that's what I want. So, but if you turn it around, you can actually prove the theorem that states that the medians first intersect at one point, and second, get cut by that intersection point in the ratio of 2 to 1, counting from the middle, from the vertex. You know the theorem, obviously, right? Did you actually prove it in high school? Using what?
It's using like Chevy's theorem, probably.
Well, the Chevy's theorem is a more general theorem than the median theorem. So did you prove Chevy's theorem? I'm not sure if you can do it by similar. So the proof is non-trivial. Proof of Chevy's theorem, well, if I remember my high school textbook, that easily took a page or more to prove Chevy's theorem, okay? The method I'm talking about, the barycentric method, is actually, it allows you to prove all these theorems in like no more than 2 lines. So if you're interested in learning this, again, it's primarily for geometric problems in math rather than physics, but it's using the concept of center of mass and its properties to prove and find things. So if you're interested, we can have a lesson on that as well. Just let me know by next time, okay? On this happy note, yeah, let me actually save this slide as well because we're out of time, but next time I can actually show you how it's done in 2 lines. Chevy's theorem's proof is no harder than this. So, okay, I'll see you on Thursday.